This is not too bad. Okay, so let's go ahead and continue with our discussion. I believe in the previous class we were done with binary subtraction. So are there any questions about binary subtraction, which is a very interesting extension of binary addition? So are there any questions, or did I remember incorrectly? We have not finished binary subtraction. Because I just watched my own video 2 days ago, and at the end, well, it seems like we got binary subtraction covered. Hmm? I think we did. Yep. Okay. So if you guys have any questions regarding binary subtraction, please bring up those questions. And I'm assuming that even if you're not reading ahead of me, you're keeping up with me. Okay? If you're not keeping up with me, unless you already know this material or you can absorb material really, really fast, I strongly suggest that you start to catch up. Okay? The best way is to read ahead of me. Okay? It may be just a half a module. Okay? It doesn't have to be the entire module. But if you know that I will be talking about signed numbers or how we represent signed values, like in today's class, it will be really helpful to wrong slide. So we are now on a signed value representation, which is right after binary number subtraction. So if you see that we finished binary subtraction in the previous class, if you read ahead of me and at least get into the module of signed value representation, I think it will help you understand the material much better in class. Is that okay? All right. So it's just a recommendation. Once again, I cannot make you to do it. I don't want to make you to do it. If you think it's going to be helpful, go ahead and do it. If you think it's not going to be helpful, don't do it. It's not my grade. I say the same thing to my own kids. So, yep. It's not my grade, it's yours. Yeah, but I get to live in this house. Yes, only until 18. All right, so here we go, signed value representation. So with this particular module, one thing that I kind of like a little seed I want to plant in your head right now, and I got my tablet working, so this is great because now I can use the tablet instead of the whiteboard, and that makes everything recordable, which I think is really cool. Okay, let me unlock it first. And let's see, we want lecture notes. All right, so another class, Monday, Wednesday. Okay, let me show you how you can see. You cannot see what I'm doing right now because I have not turned on the visor on this side. So visor is also interesting. It is actually just a Chrome extension. It is not a full app by itself. It is a Chrome extension. It won't run unless I have Chrome. But what it does is, what you're seeing is exactly what my tablet is seeing. So it's a casting or screencast app that runs on the tablet, and it only relies on a Chrome extension to see it on the PC side, which I think is really kind of cool. Okay, so I'm going to give this a name here, 1189, which is the code for the semester. Create and open. So now we have, there's a very long lag. I really don't quite understand why there's a lag, but that's besides the point at this point. So I'm going to do something like this. I'm going to use the blue color and draw one thing here. And then I'll ask you, what is that? I like that, but even that is interpretation. Okay, that's interpretation even to say that it is a line. Okay, it is no more than a bunch of pixels, right? There's a whole bunch of blue pixels, there's a whole bunch of white pixels around it, and that's it, okay? So if you want to just look at the factual things, okay, what is actually true, you can just say that, okay, the RGB values of the pixels around it is pretty close, if not at 255, 255, 255, 255. And then the RGB values of these kind of pixels that we can see that are different is probably 0, 0, and I'll give it maybe 50, okay, because it's a dark blue, okay? And that's it, okay? And then somebody's going to say, but it looks like 1 to me. It can also be lowercase l, can be uppercase I, right? What else can it be? Oh, what about that vertical bar thing, on the keyboard? Okay, we call that pipe in command line, interface. We also call it bitwise OR in C and C++. So which one is it? We don't know. Without the context, we do not know. We simply know that there's a whole bunch of blue pixels. They seem to be connected in a vertical way against a white background. That's all. Is that okay? So there is the what is presented, and then there's the interpretation. In other words, what it means depends on interpretation, and interpretation depends on context. Okay? But looking at just the representation itself, it has no particular meaning. Are we okay with that? Okay? All right. So for those of you who want a second example to illustrate the concept of interpretation, meaning, and stuff like that, just think about you're drinking coffee. Even if you don't drink coffee, think about somebody else drinking coffee. So here's black coffee, okay, and then you put cream in it, and it swirls, okay. And some people will go like, I see a certain deity in my coffee. Some people will say, I see a certain demon in my coffee. Some people will say, I see a unicorn in my coffee. Those are all interpretations, okay? Because if you have never seen a unicorn ever in your life, okay, and you don't know what a unicorn is, can you still say that I see a unicorn in my coffee? No, okay? And if you're never introduced to the concept of of a higher being and stuff like that, you cannot refer to the demon nor the deity either. So that's all interpretation. All we know is there's uneven distribution of creamer versus coffee. That's the fact. Okay? So now we get back to the slide here, because now this part it will start to make more sense. All right, so the value represented by the base 10 number, -45, is a quantity. In other words, it is representing, there's a lack of 45 of something, okay, or there's an owing of 45 of something, okay, because it's negative as a quantity. -45, okay, to spell out the characters, is really just a way to represent that quantity. Okay, because if you're not, well, okay, most people use numbers or digits like this. Okay, I cannot imagine any person not using digits like this. But the second paragraph says, but inside a solid-state binary digital computer, we don't have the negative sign. We don't have 4 or 5 either. Okay, we only got zeros and ones. Well, if you have zeros and ones, we can represent 45 just fine, okay? Because 45 is, what, 32 plus 8 plus 4 plus 1, okay? Those are the powers of 2, if you break down 45. So those would be the ones, in a binary number, and then all of the other powers of 2 would be zeros. So we can convert 45, the quantity, into a binary number just fine. Okay, that's cool. But what about to represent that it is negative? Okay. Can we use a bit, one bit to say, if this bit is a 0, whatever the rest of the number is non-negative. If this bit is a 1, the rest of the number is representing something that's negative. Yes, we can, but the problem with that approach is if you just use a single bit to flip the sign, but then use the rest of the bits to represent the quantity or the magnitude, then the adder wouldn't work correctly. The subtractor wouldn't work correctly. Okay, which is kind of a hassle. Okay, we don't want to build special adders and special subtractors just so that we can deal with the signedness of numbers. So that's the issue. That's the problem that we need to solve. Section 3 is really just a reminder. Okay, I know most of you still remember algebra enough to get through this part pretty quickly. So we are talking about arithmetic negation here. So in general, the negation of a value x is x itself. Is that okay? Making any sense? Okay, cool. And then the second one is x, whatever x is, plus the negation of x gives you 0. Okay, simple stuff that we already know. The third one is x minus y can be re-expressed as x plus and then the negation of y. Is that okay so far? All right. So this is just simple algebra stuff, but we'll get back to this after we understand how to do arithmetic negation in binary. Okay, so we'll get back to this just to say, okay, this is what I claim is doing arithmetic negation, but does it actually work? Can we validate that it does work? So section 4 is starting to be a little bit more interesting because most classes that you have, you look at values as a number line. So I'm switching back to the tablet right now because I can illustrate it. So in most classes, you look at numbers as a number line. Okay, there's a lag here, and we typically put 0 in the middle, and then you get all the positive numbers on one side, and then all the negative numbers on the other side, blah blah blah, and blah blah blah. Right? Okay, so that's a pretty typical thing that we do of a integer number line. Okay, we're not even dealing with real numbers in this class. Well, until we get to floating point numbers. But in integers, this is how we see a number line. But I would say this makes no sense whatsoever when you're dealing with integer variables in C and C++. Why do you think I say that? Yep.
They don't have the infinite range.
And why is that?
The amount of storage that you're assigning to it.
Okay. So if I give you x many bits to represent integers, how many different values can it represent? I don't even care about the range itself. I just need to know how many distinct values it can be represented. 2 to the power of x, very good. Okay, so with a 32-bit number, we can represent 2 to the power of 32 distinct values. Okay, and I'm not even talking about, oh, it is 0 to this being the non-negative values and -1 to this negative value being the negative values. We're just saying that you only have 2 to the power of 32 distinct values, and that's it. Okay, so that means the traditional sense or the mathematical notation of a number line doesn't really work that well with integers in computer science, integer variables in computer science. All right. So what do we do instead? Well, we do a number circle instead. So let me switch back to a medium thickness and black line. There we go. All right. The glare of these two monitors is killing my eyes because all I can see on my tablet is the fluorescent light. So I suppose I can tilt it a little bit, put something like under, prop it up. Yeah, that works a lot better. All right, so I'm going to draw a circle first. Okay. And we'll designate a location for 0. Okay. So 0 is basically 12 o'clock, on this circle. So depending on how many bits we're dealing with, we can chop it up into, sections. And the number of sections is going to be a power of 2. 32-bit is out of the question. Okay, and some people, people who are not in this class would say, 32 doesn't sound too bad. Well, but you're talking about 2 to the power of 32, which is 4 billion something individual segments. There are not enough pixels to do that on this screen. Okay, So I'm just going to deal with like 3 or 4-bit numbers. Okay, I'm going to choose 3-bit numbers because it's a lot more manageable compared to 4-bit numbers, given the amount of time that we have. Okay, so we'll just go ahead and chop it up into 2 to the power of 3, which is 8 individual sections or the individual lines, like so. And then we'll start to look into the bit representation for each of these slots. Okay, so the 0, which is the one at 12 o'clock, we'll just say that it is 0, 0, 0 as a representation. So the outer edge is only representing physical states in a way. In other words, the 0, 0, 0 or the 0, 0, 1 is really just saying that there are 3 adjacent gates, and then the output of those gates turns out to be low, low, low for the first one, and then it's low, low, high for the second one, and so on. So we are looking at physical states that you can actually measure using a multimeter. So we are not even concerned about, but what does it mean? Nope, there are no meanings. We are just talking about 3 logic gates, and they're outputting, low, low, low as voltage, and so on and so forth. Is that okay? All right. So the first thing we do is to go like, oh, but we know what 0, 0, 0 as a base 2 number really can represent as a quantity, right? We talked about base conversion already. So 0, 0, 0 as a base 2 number means that we have 0, 1 plus 0, 2 plus 0, 4. That ends up to be just the quantity of 0 itself. Okay, we can do that. So inside the circle, I'm writing down the quantity that we typically use that bit pattern to represent. Okay? But remember, typical. Okay? So the rest is not too bad. Okay? Is that okay? So we'll just pick one and double check, right? We'll pick 101 and ask, does it really represent 5? Why is it representing 5? There's 1, 1, 0, 2, and 1, 4. 4 plus 1 is 5. Okay, seems okay. All right, but you also notice a pattern, okay? You notice that when we go in a clockwise fashion, we are increasing by 1, and when we do it in a counterclockwise fashion, we are decreasing by 1. Is that okay? I mean, it seems to be that pattern, right? So that means if I had to pick a place to represent -1, where is that going to go? Sorry? Counterclockwise, but which -1 is going to be adjacent to what? That is already on this particular wheel. 7? It's going to be adjacent to 0, but it is going to take the place, the same slot as 7. Okay, very good. So what we'll do is we'll represent those with a red representation. So -1 seems to go there. Because if I start with 0 and I go counterclockwise 1 slot, that's where -1 is supposed to be. Okay? So using that reasoning, we can say, oh, -2, -3, and -4. Seems to make sense, right? But now we have a bigger question. So the bigger question is, if I just look at the bit pattern of, say, 110, in other words, I use a voltmeter and I measure the output of 3 adjacent gates. They turn out to be high, high, and low. Okay? Then I go like, I'm confused now, because confusion means you do not know quite which way to interpret something. Okay, there are multiple ways to look at something, and you don't know which one is the right way. That's confusion. So the confusion is it representing 6 or is it representing -2? So that might be a question that some people have. Go ahead. Say that one more time. Depends on whether it's signed or unsigned. But then I will answer that question of, is it 6 or -2 with another question. Guess what my question is going to be to respond to that original question. Why do you care? It's just three transistors, okay, or three gates, not transistors. It's just three gates that has the output of high, high, and low. Until I know what I need to do with that particular, 3-bit pattern, I don't need to know whether it is 6 or -2, or whether it's all displayed on screen as 2 white pixels and 1 black pixel, right? I mean, that's one way to use that. Or if you remember those dot matrix printers, remember those really noisy and musical printers in the past, from way, way, way in the past? No? Some of you look at me go like, what? What are you talking about? Dot matrix? Does it have to do with Keanu Reeves? The Department of Transportation and then the Matrix movie. What do those two have to do with one another? I can tell you why. Because in Matrix, the second movie, there were a lot of shooting scenes along the highway. So the Department of Transportation may need to get involved and go like, hey guys, you got to stop doing this. So anyway, dot matrix printers, okay, they have pins, okay, they have physical pins that are actuated by magnetic fields, which then are energized by electrical currents. So 110 can simply mean, oh, the top two pins are going to be contacting the ink, how do you call those things, ink cartridge, and having an impression onto the paper, and then the 0 is one pin that is not actuated, so you're not going to have one dot, corresponding to the 0 on the piece of paper. It could be just that, right? So until I know how the output of those three transistors are going to be used, I don't really need to know what it means. It is just 110. Is that okay? All right. So that is important because otherwise you will always have that gnawing feeling in your head and go like, so which one is it going to be? We don't even try to interpret until we have to interpret. Okay? So are we good so far? Okay. So the next question now is to say, but how can I figure out the binary representation if I know that I want to use bits to represent a signed value? How do I know the representation of that bit pattern? Okay, first of all, does everybody understand that question, what I'm asking? Okay, so yeah. So let me say that one more time. Okay. I think it's better if I hide this and give you another circle. So this way, I can ask that question in a slightly different way. So let me finish the circle first, and then I'll ask you the question. And then this time, I'm going to give you a 4-bit thing. Okay, one. Okay, I think I got one too many slots. That looks right. Okay, so I'm going to give you this wheel, and we got 4 bits now. And then the outer part is really just the states of our gates. Oops. 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, whoops, 1, 1, 1, 1, 0, and 1, 1, 1, 1. This is interesting because they say that, how do you know whether what your mother tongue is? Okay, if you speak multiple languages, which one is your mother tongue? It's the one that you use for counting. That's what they say. But I count in binary. Yep, kind of funny. So if I say, okay, I want to represent the value of -5, okay? Which one, and I tell you that one of these, represents -5. Okay, so I'm already telling you the interpretation, the meaning that I want to encode into the states of my gates. Okay, so I already gave you the intent. and also what value I want to represent. But now the question is, how do I find out which one of these bit patterns is representing -5? Now you can kind of use the method that I used earlier, like this is 0, -1, and keep counting that way. But that's not a very systematic way. Okay, so if I give you like 32 bits, okay, there are 4 billion of these things in a gigantic wheel, and I ask you what is the representation of negative 65,017, okay, are you going to count it on that gigantic wheel? No. So we need a systematic way to do it. Does that make sense? So even though we have an intuitive way to do it, we want to have a systematic way and use mathematics to help us find the representation given a particular value that we want to represent. Is that good? Okay. So how do we do that? So the way I'm going to do that is to go back to the wheel that is a little bit smaller, because I want to find patterns. Okay, computer science, math, engineering, a lot of those areas are all about abstraction. Okay, it's about finding patterns. So when I look at the part that has 2 values associated with a particular bit pattern, what do you see as a pattern? And by the way, because we're using 3 bits, so 8 is kind of a special number in this case. So when you look at 8, and then you look at the values, the interpretations of the ones that are capable of representing negative values, do you see a pattern? Can you like write an equation and go like, oh, that seems to be true for every single one of these slots?
The positive number plus the negation of the negative number equals 8.
Yep, exactly. So that's kind of interesting, isn't it? I find it interesting. So let me just kind of write down the summary of what we observed. Okay, so it seems like if I call the non-negative value y, and I call the negative value x, okay, for those 4 particular slots, if I say y minus x, it's always going to be 8, which turns out to be 2 to the power of 3. Do you guys agree with this particular pattern? Okay, it holds true for all of them. Okay. And as it turns out, y is the easy one. Y is really just the quote-unquote natural value represented by that binary number. Is that okay? So y is easy. Okay, once we figure out y, we're done. So now we focus on the other side. In other words, we want to move y on one side so that we look at y, we express y, which is very easy to convert into zeros and ones, and I express it using 8 plus x, x being the negative value that I want to represent. So are we doing okay so far with this? Okay, cool. And then we notice something. So because x is known to be negative, okay, so we are basically saying 8 plus the negation of negative x, right? Okay. And we know negative x is the non-negative quantities, or the magnitude of the negative number. Okay. So this is interesting. So to figure out the y, it seems like it's pretty easy to do. All we have to do is to kind of flip the sign of the negative value that we want to represent, and then just add 8 to it, and we're done. Is that right? Okay. But there's one problem, because with a 3-bit system, the adder is only 3-bit wide, which means you cannot represent 8. 8 is a value that you cannot represent using only 3 bits. Does that make sense? Because if you filled up all the bits with 1s, okay, you have 1 plus 2 plus 4, which is 7. We are still short of 8. So I got to fix that problem. Well, I can fix that problem by saying it's 1 plus 7 plus the negation of the negation of x. So I cheated. I break up the 8 into 1 plus 7 because I can represent 7. 7 is fine, not a problem. Okay? All right. So now what I need to do now is to kind of look at this in a slightly different way. So I'm going to look at this as 7 minus some quantity and then the whole thing plus 1. So the quantity that I'm subtracting from 7 is really just negative x, right? So this negative x goes here. Is that okay? It's algebra up to this point. Okay. All right. Has anyone heard of the term 2's complement? Okay, it's okay if you have not. Okay, it's not a big deal. Now, 7 minus something is very special in base 2. Let's figure out why it is so different, so interesting in base 2. Remind me again, if you want to look at the board, that's fine. Remind me again, what is the binary representation of 7? 111. Very good. Okay. So we're going to say, okay, this is 7, 111 in base 2. And I'm going to subtract a 3-bit number from 7. And the 3-bit number that I'm subtracting, since we are using negative x here, let's call it z0 for the least significant digit, z1 for the second least significant digit, and z2 for the most significant digit. Is that okay? So I'm doing the subtraction here. And go like, well, normally we have to worry about borrowing when we do base 2 or any base of subtraction. Do you think I have to deal with borrowing here when I'm subtracting from 111 but in base 2? I don't, okay? Because when you look at the borrow function, if I do you remember the borrow function? The borrow function is a 1 if and only if x is a 1, is a 0, and y is a 1. So knowing that x is a 1 to begin with, there's no way that I would end up with a borrow of 1. That's the first good news. The second one is going like, okay, so knowing that we won't have any borrows, okay? What is 1 minus 0, z0? Okay, so I'm just going to write down, the typical answer here is just 1 minus 0, right? But z0 is also a bit. In other words, z0 itself can either be a 0 or a 1 as a value, right? Okay. So what if z0 is 0? 1 minus 0 is a 1. And that seems to be just the negation of z0, right? What if z0 is a 1? If z0 is a 1, 1 minus 1 is a 0. Hey, that means the result is also just the negation of z0. So instead of using 1 minus z0, which is arithmetic, I can just say, oh, that's an easier way to say it. It is just the negation of z0. Same thing is going to apply to the negation of z1 and the negation of z2, right? How do you call this operation in C and C++? It's called a bitwise NOT. Okay, it's called a bitwise NOT, which is using the symbol on the keyboard. It's the tilde symbol that is going to do this. It's a unary operator because you only need one thing to operate on. Everything that was 1 turns into zeros. Everything that was 0 turns into 1. Is that okay? So 7 minus negative x is easy to do because now we can call this part C1 or 1's complement of negative x. I just use this notation for 1's complement. If you prefer, you can replace C1 with a tilde symbol because that's bitwise NOT in C and C++. Are we doing okay so far with this? We still need a plus 1 because the negation doesn't really take care of the plus 1. So we still need this plus 1 on this side. Every time you take the one's complement of something, or the bitwise not, they mean the same thing. One's complement is the same as bitwise not. Every time you take the one's complement of a bit pattern and you add 1 to it, guess how we call that operation? 2's complement. So this is 2's complement. So y, which is the 2's complement of negative x, is the 1's complement of negative x plus 1. And x is the negative value that we want to represent, which means negative x is the magnitude of the number that we want to negate. Let me say that one more time because that's a lot of terms right there. X is representing the negative quantity that we want to represent, which means negative x is the magnitude of that negative value. All right? Okay? So that means 2's complement is actually used to represent negation itself, arithmetic negation. Yep. Yes. Bitwise not. Yeah, it's not just negation, it is a bitwise not. Yep. You can look at it as a multi-bit NOT gate. It would do the same thing. So are we okay so far with the derivation or how we got to this point? Y is the bit pattern that we want to find. X is the negative value that is of interest to us. And this calculation here is how we mechanically figure out the bit representation of a negative value. Well, this is all pretty abstract. Let's actually go through this as an example, okay? And we'll use 4 bits as an example. Okay, so what I'll do is I'm gonna select this block here, and then we copy and then paste it in onto the second page. So let's see, how do I paste here? Nope. I can't remember how I paste. Oh, maybe I just drag it. Yep, there we go. Okay. So I want to drag it over here because I want to plug in some values, okay? Remember, it was -5 that we want to find out, right? What is the bit representation of -5? So we'll plug that in and see whether we can figure it out, okay? So we'll say that y, oops, I have to change back to the pen tool. So y is the 1's complement of the negation of -5 plus 1. Is that okay? There's double negation because x itself is -5, but there's a negation here. Okay, that's not too bad. So C1 is really saying 5. Okay, because double negation cancels out. And then we look at 5 as a 4-bit number. 0101 in base 2 is how we represent 5 in base 2. And then because you can't really do 1's complement unless you're dealing with a binary number, so that's why we have to convert the quantity of 5 into its binary representation first before we can apply bitwise not. Okay, but once we have the 0101 representation of 5, now we can apply 1's complement, which is really easy because we just turn all the 1's into 0s and all the 0s into 1. Okay, so this becomes 1010 in base 2 plus 1. Okay, that becomes 1011 in base 2. Done. So what this is saying is 1011 in base 2 should represent the quantity of -5 if that is what I want to store in the system. How do we check whether that's making sense or not? Well, we can, with this smaller value, we can just kind of count, right? So this is -1, -2, -3, -4. This is -5. We have a match. So that is how we represent negative values, is to apply 2's complement to the magnitude of the negative value that we want to represent. Is that okay? So are we, yeah?
That little 2, the subscript, is that representing the base 2?
Yeah. So the subscript of 2, is to emphasize that we are dealing with a base 2 number. Yep. Cool. So now I'm going to do one more thing, okay? So I'm going to make a very bold claim to say that to take the negation of x is really doing the same thing as the 2's complement of x. I'm equating these two operations and say they mean the same thing when you're dealing with a fixed number of bits. Okay, in this case 4. So does everybody understand what I'm claiming? I'm claiming that by performing 1's complement plus 1, I'm really doing the same thing as arithmetic negation, which changes the sign of a magnitude. That is a pretty bold claim. Prove it, right? Well, I can't mathematically prove it, not in this class, but I can show you a few examples to convince you that, yeah, it seems to make sense, okay? So what we'll do next, I'm going to open the new slide here, is to look at a few properties of negation. The first property of negation is if you take the negation of x, you get x back. There's a terrible lag, between what I write and what is reflected, but that's basically what I'm saying. So if 2's complement is doing the same thing as negation, it should have that property. Okay, so we'll check it out. So C2 of C2 of some bit pattern should get us back to x. Is that okay? So we'll say, well, we'll use a concrete example. What about that thing about -5? Let's take 2's complement of -5 and then take the 2's complement of that. We should get back to -5. Okay, so that's 1011 in base 2. Okay, so this is the 2's complement of the 1's complement of 1011 in base 2 plus 1. That becomes the 2's complement of 0100 in base 2 plus 1. That becomes the 2's complement of 0101 in base 2. That becomes the 1's complement of 0101 in base 2 plus 1. That becomes 1010 in base 2 plus 1. And that becomes 1011 in base 2. Woohoo! We get the same bit pattern back. Not a problem. Good sign. Okay, this is a good sign. Okay, this works out. Let's try something else. Let's try to add a number to its 2's complement and see if we get 0 back. Okay, so this time we'll say, okay, 0101 in base 2 plus the 2's complement of 0101 in base 2. That should give us all zeros. Okay, so we'll work this out. Okay, and I'll just kind of expand what we already know. 1011 is the 2's complement of 0101 in base 2. And most people look at this and go like, Tag, you got to be wrong here. Well, but remember, whenever we deal with a 4-bit number, every operation is going to be 4-bit wide, including addition. So when we perform this addition, I'll do it on the side here. 0101 in base 2 plus 1011 in base 2. Okay, so we'll do the double half adding mechanism. And this is a 0 for K0. Okay. Let me close this first. Let me close this screen here. And what I'm trying to do is I'm trying to reduce the lag Because the way it is right now, the lag is just killing me because I can't talk about something until it appears on the screen. So I'm gonna change that property. I've been trying to experiment with this to figure out what would help reduce the lag, and so far I have not had any luck reducing the lag. So we'll try that because that's what it was last year, and it did not seem to have this problem last year. So we'll move. The dialog box is too long. I can't see the bottom. There we go. And then we have to move it down again. So I can click on the device. And it will crash the first time, and then the second time it's going to work. But I'm not sure whether the lag is going to reduce. Doesn't seem like that setting should have anything to do with it, but we'll try. Okay, so now okay, I know what to do. Use the mouse pointer on the PC itself because that's instantaneous. So we have 1 plus 1 being a 0 with a carry. Okay, so we have a 0 and a carry. And then we have, it doesn't really help with the lag. So then we have the 0 plus 1, which is a 1, okay? And then we have this 1 plus 1, which is a 0 with a carry. And I also backfill this 0 here. And then we have 1 plus 0, which is a 1, okay? And then we have this 1 plus 1, which is a 0 with a carry. And then once again, we have 0 plus 1, which is a 1. And then we have 1 plus 1, which is a 0, with an overall carry. There we go. See? I said it was 0, and it is 0. It's just having an overall carry, but that overall carry does not count as the result of the addition. Okay? So this is the important part when we look at fixed bit width representation, is every operation, addition, subtraction, and whatnot, we only limit to that number of bits. Okay? So right now, we are looking at 0101 plus 1011 being 0000, but with an overall carry. But the overall carry has no particular meaning at this point, okay? So, getting back to here, it does work out. Is that all right so far? Okay. So the third thing that we mentioned about negation is if I want to compute x minus y, the other way to do it is to say x plus and then the negation of y. So I want to substitute that negation with 2's complement and see if it works out the same way. So that's my last test. So let's go ahead and use a different example. So this time I want to compute, I don't know, let's try to compute 5 minus 6, okay? All of these values can be represented in 4 bits. Okay. So I claim that this is the same thing as 5 plus the 2's complement of 6. That's my claim. So this question mark, there's a little question mark here because I'm really testing, are they really the same thing? We want to find out. So now we look at this and go like, okay, this is 0101 in base 2 because that's how we represent 5 in base 2. Plus the 2's complement, okay, this is just plus, the 2's complement of 6, which is 0110 in base 2. Becomes 0101 in base 2 plus the 1's complement of 0110 in base 2, the whole thing plus 1. Okay. And we flip all the bits. 0 turns into 1, 1 turns into 0. So we have 1001 in base 2 plus 1. So we end up with 0101 in base 2 plus 1010 in base 2. So this one is rather easy. I did not really intend it to be like this, but it just turns out to be that easy. Because everywhere we have a 1 on the left-hand side, there's a 0 on the right-hand side, and vice versa. So that means the sum is just 1, 1, 1, 1 in base 2. 1, 1, 1, 1 in base 2. Well, is it working or not? Because 5 minus 6 is supposed to be -1 as a quantity. So now the question is 1, 1, 1, 1 in base 4, in base 2, 4 bits, representing -1? What do you think? There are two ways to double check this one. Okay, the first way is kind of more visual, because we go back to the number wheel and go like, if I go counterclockwise one slot from 0, do I get 1, 1, 1, 1 back? That's the first kind of more visual way to do it. Yep, that kind of works out. But the second way is to reapply 2's complement and say, if I take the 2's complement of 1, 1, 1, 1 in base 2, do I get 1 back? Because if that is the case, that means 1, 1, 1, 1 is legitimately the representation of -1. Okay, so we'll try that. Okay, so we go all the way back here, and then we say, okay, what is the 2's complement of 1, 1, 1, 1 in base 2? Yep, we'll do it really long and slow, okay? It's like smoking. Not cigarette, but food. Okay, so 1's complement is flipping all the 1's to 0's. So we get 0, 0, 0, 0 in base 2 plus 1, and that turns out to be 0, 0, 0, 1 in base 2. Woohoo! It all works out. So 2's complement is very interesting because everything that we knew about adding and subtracting with all those 3 by 3 bit carry look ahead thing and borrow look ahead subtractor and stuff like that, they all work with 2's complement. We do not need new circuitries for adding nor subtracting. It all works out. Which adds to the confusion of, so when do we really need to know whether we are dealing with 2 or -2 or 6? Because even addition and subtraction doesn't care. It's like, yeah, you can give me anything, whether it's signed or unsigned, it's the same mechanism. So when does it count? When does it matter whether a bit pattern like 110 is really representing 6, which is a positive quantity, or -2 as a negative quantity? Let's go back to that slide a little bit, just so that we can visualize and see those things on the screen. So when do you think it matters whether this is representing 6 or whether it's representing -2? The bit pattern 110. I give you a clue. It has nothing to do with addition or subtraction, but it has to do with comparison. Okay? So now the question is, okay, now I'm going to slide all the way back to an empty area, which I don't have anymore, so I'm going to open a new slide. So the question is, if I have 1, 1, 0 on one side, and I have 0, 0, 1 on the other side, and I want to know whether it is less than or not, then I have to answer that question. I cannot defer any further, okay? At this point, I have to say, okay, in order for me to answer this question, you, the programmer, has to answer this question, okay? Are we dealing with signed numbers or unsigned numbers? Because if we're dealing with signed numbers, then 110, which is representing -2, is in fact less than 1. Okay? On the other hand, if you say, no, we never have to deal with negative values in this particular code, so we're using unsigned integers, then 110 is representing the quantity of 6. 6 is less than 1 is false. That is when it matters. because now it is interpretation. Is that okay? So this is really counterintuitive compared to C and C++ programming. Because in C and C++ programming, what is the first thing you need to know about a variable when you declare the variable before you even initialize just the declaration itself? What do you need to know? Whether it's signed or not, right? If it's int, it is signed. If it is unsigned, it is unsigned, right? And then you do all the calculations. Initialization to 0, okay? Int x or unsigned x, and then in somewhere else you say x equals to 0. Do you think that really matters whether it's signed or not? No, because we are just putting zeros into every single bit of x, okay? Signed or not doesn't really matter, okay? And then the next statement says, x plus plus, okay? Does it really matter whether x is signed or not? No, because it goes through the same adder to go to add 1 to whatever x had to begin with. Doesn't really matter. It's only until you say, oh, I need to check the boundary. Is x less than something? Then it matters. Is x greater than something? Then it matters. Okay? So in C and C++ programming, you're providing information a lot of times way before you need that piece of information. But in assembly language programming, which we'll do in the second half of these 16 weeks, we defer all of that, okay? You cannot even say something is signed or unsigned. You can only say, after a comparison, what do we do about the result of the comparison? Okay, that is when it matters. So are we okay so far with signed number representation? Yes? Okay, very good. I'm looking at the clock. We got another 10 minutes or so. So that means we can move on to another module. And guess what the next module is going to talk about? Comparison. Very good. Seems logical. So now we're moving on to binary number comparison. And this particular module obviously is an extension to the one that we just talked about because comparison relies on subtraction. But before we go even there, we'll just say that with all the comparison operators that C gives you, you really only need one. Okay? If you have less than, you can redefine all of the other comparison operators using just less than and logical operators. So this is just a table to show you why that is the case. So if your original expression is x is less than y, okay, no change is needed because less than is implemented. Okay, cool. If your original comparison is to see whether x is greater than y, we can just transpose the variables or the expressions and it's done. Okay, no big deal. If your original expression is x is less than or equal to y, or whether x is less than or equal to y, then your new question is it not that y is less than x? Can you see it's really meaning the same thing? Okay? Might take you a little bit of time to kind of adjust to the alternative representation. The other one is whether x is greater than or equal to y. Well, that one is easy. We just transpose x and y compared to the previous one. So x is greater than or equal to y is really the same thing as it is not the case that x is less than y. Kind of makes sense. Okay. What about not equal to? Well, not equal to is a little bit longer. It becomes x is less than y or y is less than x. Right? In fact, in some programming languages like SQL, the representation of not equal to is less than or greater than. Okay? Pascal has that representation as well. What about equal to? Well, if you know how to represent not equal to is the negation of that. There you go. In other words, next time you're taking this class, so you may still be taking 400 or 430 in the future, right? Or in the same semester. So you can now write your C programs only using the less than operator without using equal to or not equal to or greater than or equal to or less than or equal to.
To make it harder for anyone who wants to read the table.
just to impress Professor Fox or Iraj Sapsaveri.
Now, does that also mean you can do it with the greater than?
Hmm?
So does that also imply that you can use the greater than
Yes.
symbol?
Yep. Well, if you have less than, okay, I'm just thinking about less than or equal to, would that be sufficient? No, because you cannot differentiate whether it's really less than or equal to, and there are no further ways to separate those cases if less than or equal to is the only thing that you have. So less than or greater than by itself is sufficient. But hold on a second here, okay? If you really want to go minimalist, okay, then you go like, we don't need no stinking not or stinking, or. We just need the global almighty NAND, right? So now you can write all of the conditional expressions using only less than and NAND. All of the other stuff is fluff, man. You don't need that stuff. Sure, it's handy sometimes, but you don't need it. So are we convinced that if I can just decide whether a bit pattern is less than another bit pattern, it's sufficient. Okay, I can work everything else out from this. Is that okay? Okay. Well, this is important because this gives me the freedom to only talk about less than and not to worry about all of the other comparison operators. So I can focus on just one thing. Okay, is x less than y? That's all I need to know. All right? Okay. So we'll go ahead and look at unsigned comparison. In other words, if you're comparing two unsigned bit patterns, how do we do that? So there's a little bit of math here, and everything is based on these two observations. Okay. Can everyone agree that 0 is less than 1 is true? And then all the other bit patterns would be false because 0 is less than 0 is false, 1 is less than 0 is false, 1 is less than 1 is false. I only point out some of the more less obvious ones, but 0 is less than 0 is false is also obvious. Okay. So what we're going to do next is we will look at the value represented by a bit pattern. Okay. So for notation purposes, we'll use the same notation. X with a subscript of I is representing the ith bit of a multi-bit number x, and the same thing for y. So y subscript I is the ith bit of y, which is a multi-bit number. Okay. So we know that xi as a digit, as a 0 or 1, is representing the quantity, which is basically just the presence or the absence of 2 to the power of I of the value represented by x as a whole. Is that okay? Does everybody understand the nomenclature or the naming of these things? Okay, it's consistent with all of the other modules. Okay, it's just that I need to make sure that we all understand what this is all talking about. So x is a multi-bit number. Xi is designating a particular bit, the bit at position I, and that is in return is indicating the presence or the absence of 2 to the power of I of the value represented by x. Okay? So all of the notation is consistent with the other modules. We also know that 2 to the power of n is greater than the summation of I going from 0 to n minus 1, and then the terms that we are summing are the 2 to the power of I. Okay. So let me expand this one a little bit and see if it makes sense to you. So what we are doing, what I'm claiming is 2 to the power of n is greater than 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus blah, 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 2 to the power of n minus 1. I'm just spelling out the sigma. Okay? This is what I'm claiming. And what are you going to do? Yeah, it sounds like it makes sense. No. No, we need to prove this, okay? But how do we prove it? There are many ways to prove this. So we'll choose a way that is suitable for this class, okay? So what we need to do is, well, okay, I take it back. This is something that you will definitely learn in CISP 440, but I'm going to mention it anyway, okay? It's called proof by induction. Proof by induction is really cool because what it does is you have to show me a quote-unquote base case, okay? So the base case usually is just saying, okay, let's stick a very small number into the variable in the claim that we are making, okay? So in the claim that we're making here, n, is, it can be 1, 2, 3, 4, and so on. So the smallest value that makes sense in integers for n is n equals to 1. Okay, fine. We plug in n equals 1 and see what happens. When n equals 1, then 2 to the power of 1, which is just 2, right, is greater than the sigma notation. How long is the series on the right-hand side? Only has got one item, right? And that one item has I being what? 0. So now the question is 2 to the power of 1, which is 2, greater than 2 to the power of 0, which is 1? Yep. 2 is greater than 1. No big deal. Okay, that's the base case. Once the base case is done, what we do is now we perform the induction step. The induction step is interesting because it has an assumption. It makes the assumption, the induction assumption in this case, is to say, let's assume, okay, that 2 to the power of k for some k is known to be greater than sigma I equals to 0 to k minus 1, 2 to the power of I. In other words, the theorem is known to be true when n equals k. How do we know that? It's an assumption. Okay? So now the question is, based on that assumption, can we lead to the next step up, which is 2 to the power of k plus 1 is greater than sigma I equals to 0 to k 2 to the power of I. In other words, if I know that the theorem is true for n equals k, can I prove that the theorem is also true for n equals to k plus 1? Can I take that one step ahead? Just one step. That's the question. So the proof of that is it's relatively easy because all I do here is to say 2 to the power of k plus 1 is really just 2 to the power of k plus 2 to the power of k. Is that okay? All right. So on the other side, I'm not changing anything. But then I go like, oh, let's subtract 2 to the power of k from both sides. So on the left-hand side, we only got one of the 2 to the power of k's left. On the right-hand side, oh, I just need to change the index. It used to stop when I get to 2 to the power of k. Now it can stop at 2 to the power of k minus 1. Right? Wait, we know this is true because it is our induction assumption. This is how we prove that this, from here, we can now prove that this theorem is true regardless of the value of n. As long as n is 1 or more, the theorem is going to be true. I don't see any dramatic reaction from you guys. I was sort of expecting kind of like, whoa, that is cool. Keanu Reeves comes to mind. I can see the AR Keanu Reeves sitting back there going like, whoa. This is profound. Okay, the more you get into recursion, the more you start to appreciate proof by induction. Because what is recursion? It's a subroutine calling itself. But usually it doesn't call itself with exactly the same parameters that it got. Typically, something is changed when it passes those parameters along. And the technique of proof by induction works really well with recursive subroutines. You prove the base case where it stops recursion. Okay, you prove that the subroutine works in that case first. Then you go back and you just say that assuming it works, okay, the subroutine, the recursive part works, I just have to prove the part that is performing the recursive logic is also going to work. Okay, so this is really cool because now we have that conclusion. So what is that conclusion going to help us? So this is what, so given x and y have m bits, okay? So m explicit bits basically just says it has m bits. We can assume xi equals yi for some I that is greater than or equal to m. In other words, um, x, x, xm equals to ym, xm plus 1 equals to ym plus 1, xm plus 2 equals to ym plus 2, and so on. So we are basically saying, okay, from a certain digit on to the left-hand side, all the digits are identical. Okay. What if the two numbers are actually different? Well, then I is going to be greater than m, just one more than m. Because if you're comparing two 16-bit numbers, okay, and all 16 bits are different, is that okay? I can still claim that x16 equals to y16 equals to 1, equals to 0. Because those leading zeros are just implicit. They're always there. It's just that they're not explicitly represented in a 16-bit number. Is that okay? All right. So I don't have a problem finding this particular value of m. After all, the processor has a fixed width, blah, blah, blah. So we're going to use the notation. This is the notation. I don't think we actually need to use the notation here, but we'll go ahead and explain it. X and then in subscript p dot 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 to 0 simply means that we're looking at a portion of the number x from bit 0, which is x subscript 0, all the way up to x subscript p. So we are looking at p plus 1 digits of that number, the least significant p plus 1 digit of a particular number. I don't think we'll need this notation because I put it here, but then later on I did not end up using it. So the first thing we do is we make an assumption that we find a p such that xi equals to yi for every I that is greater than p. So this is a claim that is always true. Okay, it's just a matter of what p is we are talking about. So let's say we're dealing with a 64-bit number. So x is a 64-bit number, y is a 64-bit number, and they are completely different. Those two 64-bit numbers are entirely different. Okay. So that means bit 0 to bit 63 are all different. Okay? What about the implicit bit 64? So when I equals to 64, xi, yi are all going to be the same. Because those leading zeros on the left-hand side of a number, all of those leading digits are all zeros. So they're all the same. So I can always find a p to make this condition true. Is that okay? All right. So then the next one says, if xp, so basically p becomes the p is the largest number where xp and yp are different. Is that okay? So how many ways can they be different? Well, xp is 0 and yp is a 1. That's one way. Right? So if that is the case, then x is less than y is true because of the theorem that we have just proven earlier. Does that make sense? It's because y has a component that is 2 to the power of p. Even if x has all ones all the way up to, but excluding digit p, it would still be less than y. That's why we had to prove that earlier small theorem, because now I can stop and go like, yep, x can have all ones, on the right-hand side of digit p, and x can never catch up with y. Now, this is something that's obvious to you, right? If a more significant digit is a 1 on one particular number and is a 0 on a different number, then the first number is going to be the larger one. Okay, it makes sense intuitively, but can you prove that is the case? Just because something is intuitive doesn't mean it is true. Okay? So I have just eliminated any doubt of, oh, well, it kind of makes sense and it generally is true, but are we really sure that it is true all the time? Yes, it is true all the time. So the second case is when I is 1 and when xp is 1 and yp is a 0, then x is less than y is false, also due to that theorem that we have proven earlier. What if p equals to 0? In other words, I cannot find anything that's different. Okay, p equals to 0 means I cannot find any digit that is different between the two numbers. Then x is less than y is false because the two numbers are actually identical. They have identical bits all the way from bit 0 all the way to bit m. I cannot find anything that is different between the two bit patterns. So in that case, it is they are the same number, and the same number cannot be less than itself. And then we just kind of, if p equals to 0 is false, then we go back to the beginning. In other words, we just keep scanning the digits from your left to the right until we find something that's different. Is that making any sense? So this is to explain how unsigned comparison is going to work. It's not something that is really new to you because you know how to compare numbers, right? If I just write down, I don't need to put this on the tablet because we can just look at this. So if I say, one number is 63, and the other number is 58, you know that 63 is less than 58. But why is it the case? By just looking at the digits. You never think of it that way, right? This is just to explain that, to prove that, yep, that method of comparing numbers work. So are we doing okay so far with this? All right. So we are definitely running out of time in the classroom, so we'll move on to the lab because we have a second lab today. I hope you guys saved the file from the previous lab because we're going to continue from that one. It was written in the notes, in the previous quiz that you have to save it. All right, so we'll go head out to the lab, and you guys, the last person out can let the next class in. Yep.